Ohm's law helps us figure out the relationship between the voltage across a resistor and the current flowing through it. It specifically states that if you have a resistor, like this one here, so the voltage across it, V, and the current going through it, I, are directly proportional with this particular relationship in here. So it states that V equals I times R. And of course, because it relates current and voltage in one equation, that means passive sign convention applies. Similar to what we've seen before, we have seen that P equals IV, and that's why we use passive sign convention for the power. So in here, it tells us exactly the same thing. And we analyze it and we target it in the same exact way. So in here, we'll see that the I current is hitting the positive terminal first. So that means we have to use positive in this particular case. This is correct. But if for some reason or another that the current was not like this, it was actually in the opposite direction, let's call it I prime. If it was I prime, not I, even though it's just the direction is different. So that means the current is going to go somewhere in the circuit and come back and hit the negative port first. So if that was the case, then Ohm's law tells me V equals negative I times R. So it is the same, it's still directly proportional, it is still linear, it's just the sign is based on passive sign convention. So you have to take a look at the current and figure out whether it's hitting the positive first or hitting the negative first. And based on that, you use positive or negative. So Ohm's law relates the voltage across and the current going through a resistor. But what's a resistor? Well, to answer this particular question, I have to define electric resistance. So an electric resistance is the capacity of a material to resist the flow of electric charge. So assume that you have some sort of a material and you're trying to pass a current through it or a charge. Its capacity to resist this particular charge or the particular flow of charge is what we call an electric resistance. And typically we model it using a resistor. And frankly speaking, we can buy resistors ready off the shelf. They come in all sorts of shapes and sizes and values, and they come actually in standard values. So in here I'm showing you a few examples of them. Sometimes they come in carbon, sometimes come in metal thin films, sometimes they come in surface mount devices that you can't put on a breadboard. You have like specific way to solder it. But in any way, in all these cases, for circuit analysis purposes, we take a look at the resistor, we're using this particular symbol. And we typically use R to represent resistance, and R has a unit, and that unit is usually ohm, following Ohm's law, the guy that related the voltage and current across that resistor. So ohm, of course, it comes in kilo ohms as well. We've seen it in milli ohms, maybe mega ohms, and so forth. Like it comes in all different values. Also, you might see something that we call G, which is conductance. So we have resistance, and we have conductance. And conductance is just simply the reciprocal of the resistance. And its unit, well, typically I use Siemens, so you will see me writing Siemens in here, or sometimes just for Siemens, millisiemens, microsiemens, kilosiemens. But also you might find it elsewhere written as mho, okay, which is just simply the reciprocal of ohm. It's just ohm, just basically flipped. Sometimes you have it actually spelled out as mho, okay? So MHO, which is basically the opposite of ohm, like if it's reciprocal. This is ohm, well, it's like if you read it that way, it becomes mho. In any way, you can see it in R or G. So for purposes of Ohm's law again tells me that if you have some sort of a resistor, that means the voltage and the current across it are linear. And to draw this here, you will see that it's simply just a line that actually its intercept is the 0, 0 point. So this is the line that tells me that where V is V, or how I and V are related to each other. Of course, if I have a higher resistance, if you have a higher resistance, that means you have less current. That means you will have here in here, that particular case in here tells me that the resistor is higher resistor, higher I. Okay, and of course if you have a lower R, you will get something like this in here. That becomes a lower R, okay, lower value of R. In any case, it's just a simple line that passes through the 0, 0 point. So depending on the value of R, it might move up or might move down because R is just simply the slope. And in extreme cases, for example, if R happened to go to 0 value, that means according to this particular equation in here, if R is 0, that means it tells me that V is 0. Pretty much I'm going all the way down in here. That's basically what it tells me. But in circuit term, that's simply just a short circuit. So if R is 0, I'm just telling you that V across a wire, because there's no resistance anymore, is just simply 0. So plus minus in here, this particular V is 0. So the voltage across 2 points on a wire is just 0. There's no voltage difference. That's what it tells me. And the current can be anything. And as this particular diagram, it tells me like the current can be here, here, and here. In all these cases, the voltage is 0. The other extreme case, which is here, if R happened to go to infinity, that means if I just rearrange the terms of these here a little bit, I will know that I equals V divided by R is also 0. And in this particular case, the I is the 0. So if you think about it this way, this here is the I is 0. The voltage can be anything. And if we represent this in a circuit diagram, this will happen to be an open circuit. So in an open circuit, the voltage can take any value, but the current I is going to be 0. So let me just re-emphasize this. This is what we call a short circuit, okay? And we'll see it throughout this course. And this is what we call an open circuit, okay? So in a short circuit, the voltage is 0. In an open circuit, the current is 0. Now that we know what Ohm's law is, we can use it to compute the power dissipated in these type of resistors. So I'll show you a couple of cases. So here's the first case. So let's assume that I have a resistor in here. I called it R. The voltage across it plus and minus is V, and the current flowing through it is I. And in this particular case, Ohm's law tells me that voltage across a resistor is just simply I times R. And based on passive sign convention, the current is going that way, so it's hitting the positive first. So I just have to use positive. Of course, I can rearrange these to tell you that the current is simply V divided by R. So to compute the power dissipated in this R, all I have to do is just use power equals I times V. And again, it has to be positive because it's the same thing. I is actually going through to the positive first. So passive sign convention tells me that you have to use positive. Of course, we can substitute with the value of V in here. Okay, so substituting this tells me that the power can be computed as I times R, which is simply I squared R. Okay, or I could have just, instead of doing that, I could have just taken the I and just put it in here. So another way to compute the power is P equals V divided by R times V, or just simply V squared divided by R. So these are the two ways we can compute the power. So power is either I squared times R or V squared divided by R. And in both cases, I want you to pay attention. So this is a squared pattern. So no matter, this is a square of a value or a number. So it's always positive. I don't care what the value of I. It could be negative. Its square is positive. And of course, R is just a resistance, and a resistance is typically a positive value. The same goes in here. This is the square of a value. So regardless of the actual value of V, if it's -5, -3, I'm taking its square and it's R. So in both cases in here, I'm telling you that P is greater than 0. That means it's always consuming power. So there's always power gets dissipated in the resistor. So I'll do this similar type of analysis in here, but in this particular case, I'll change it slightly, and I'm just going to say, here's the resistor, here's R, and I'm going to tell you positive in here, negative in here, that's V. But in this case, I will flip the I. So technically, I can write it this way in here, or I can write it that way in here. What I'm doing in here is I'm making I hit the negative port first, so that I can show you the other way we can write passive sign convention. So again, V equals negative I times R this time. Okay, or I can rearrange these terms and I can tell you that I is simply negative V divided by R. All right, to compute the power is negative I times V because of passive sign convention. Of course, I can, again, similar to what we've done a few seconds ago, we can take that V in here, substitute it, basically that here, and we substitute it with the negative. So I have a negative I, and the V is also negative I times R. And if I actually just open this up, this becomes I squared R. That's the P. Another way to do that is just to take, you see this I in here, I'll just substitute it in here with the sign. So another way to do it is negative. Well, that's negative V divided by R times V, which is just simply V squared R. And if you pay attention to this in here and that, you will see that they're exactly the same value in here, both of them, I squared R, V squared divided by R, regardless of how the current flowing. And in both cases in here, even in this case, you will see that the power is positive. That means the resistor is always consuming power. So as it turns out, that resistors cannot generate power. They always consume power, and that's something that you have to pay attention to. So to summarize power, so power of a resistor, if I ask you to compute the power of a resistor, of course you can use I times V with passive sign convention, negative or positive, or you can regardless of what the current and the voltage values is and how they're flowing, you can just tell me it's simply I squared R, or it's also V squared divided by R. Sometimes you will see that this R is written as a G, remember the conductance, so we can just basically say, well, it is simply V squared times G, the conductance, which is just simply 1 over R. It's also worth noting that the power dissipated in a resistor is not a linear function of I, and it's not a linear function of V, and we'll use this observation later in the course.